Hello, everyone. In this section of electronics, we will introduce the operating concept of metal oxide semiconductor field effect transistors, or MOSFET devices. The figure on the right shows the structure of an enhancement type N MOSFET fabricated on a P-type semiconductor substrate. It has two heavily doped N+ regions used as the source and the drain. These two N+ regions form two PN junctions with the P-type substrate. In normal MOSFET operation, these PN junctions are usually kept reverse biased. The middle part of the MOSFET is a metal oxide semiconductor capacitor structure. A thin silicon dioxide layer is used as the insulating dielectric of this capacitor. A MOSFET has four terminals: gate, source, drain, and body. In many circuit applications, the source and body are shorted together. The distance between the two N+ regions is called the channel length, L, which is the spacing between source and drain. The device width is denoted by W. When all four terminals of the MOSFET are grounded, as shown in the figure, the source and drain inside the semiconductor substrate behave like two back-to-back PN junctions connected in series. Depletion regions exist at these PN junctions. For the details of depletion regions, you can review the earlier section on an unbiased PN junction. If a drain-to-source voltage, VDS, is applied while the gate voltage is 0, there is still no conducting path between source and drain. This is because the two back-to-back diodes between source and drain block current conduction. Now suppose both source and drain are grounded and a positive gate-to-source voltage, VGS, is applied. In the MOS capacitor structure, the majority carriers in the P-type substrate are holes. These holes are repelled away from the semiconductor surface by the electric field produced by VGS. As a result, a depletion region, also called a space charge region, is formed under the oxide. As the gate voltage VGS continues to increase, minority carrier electrons in the P-type substrate are attracted toward the semiconductor surface. When enough electrons accumulate under the gate oxide, an N-type region is effectively formed at the surface. This region connects the source and drain and is called the channel. It is also called the inversion layer because the surface was originally P-type but is inverted into an N-type region by the gate voltage. The minimum gate voltage needed to attract enough electrons to the surface and form a conducting channel is called the threshold voltage, denoted by VT. A typical VT value is roughly between 0.1 volts and 1 volt. When VGS is greater than the threshold voltage VT, a channel is formed between source and drain. If a drain-to-source voltage, VDS, is then applied, electrons flow from the low potential source to the higher potential drain, producing the conducting current IDS. The conventional current direction is from drain to source because current is defined in the direction of positive charge flow, opposite to electron motion. The drain current ID and source current IS have the same magnitude and are both the channel current IDS. Ideally, the gate current IG is 0 because the gate is insulated from the channel by the oxide layer. Because the gate and the channel are separated by the oxide, they form a parallel plate capacitor. A positive gate voltage attracts negatively charged electrons into the channel. Since the conducting channel is made of negative carriers, the device is called an N-channel MOSFET or N-MOSFET. The amount of charge in the channel is controlled by the gate voltage VGS through the electric field across the oxide. A larger VGS produces a stronger electric field, attracts more channel charge, and increases the conductivity of the channel. This is the idea behind the name field effect transistor, or FET. The channel conductivity is controlled by an electric field. When VDS equals 0, every point along the channel is at 0 volts, so the voltage across the oxide is uniform and equal to VGS. As just described, VGS must exceed the threshold voltage VT before a channel begins to form. The amount by which VGS exceeds VT is called the overdrive voltage, VOV, so VOV equals VGS minus VT. For an N-MOSFET device, the threshold voltage may also be written as VTN. Since capacitor charge follows Q equals C times V, the magnitude of the total channel charge is absolute Q equals C oxide times W times L times VOV. Here, C oxide is the oxide capacitance per unit area, with units of farads per square centimeter. C oxide equals epsilon oxide over T oxide, where epsilon oxide is the oxide permittivity and T oxide is the oxide thickness. For silicon dioxide, epsilon oxide equals epsilon R times epsilon 0. If T oxide is 4 nanometers, or 4 times 10 to the negative 7 centimeters, then C oxide is about 8.63 times 10 to the negative 7 farads per square centimeter. When a small drain-to-source voltage VDS, about 50 millivolts, is applied, electrons travel from source to drain, while conventional current flows from drain to source. The total channel charge is absolute Q equals C oxide times W times L times VOV, so the charge per unit channel length is absolute Q over L equal to C oxide times W times VOV. The drain-to-source voltage also creates a lateral electric field, whose magnitude is VDS over L. The electron drift velocity is μn times that electric field, or μn times VDS over L. Therefore, the drain current ID equals charge per unit length times drift velocity. This gives ID equals μn times C oxide times W over L times VOV times VDS. For small VDS, the drain current equation is ID equals μn C oxide W over L times VOV times VDS. This shows that ID is linearly proportional to VDS, so the channel behaves like a resistor. The channel conductance is GDS equals ID over VDS, which equals μn C oxide times W over L times the quantity VGS minus VTN. The first factor, μn C oxide, is determined by the process technology and is defined as Kn prime. Its unit can be converted to amps per volt squared. The second factor in the channel conductance is W over L, called the aspect ratio of the device. The product of Kn prime and W over L is defined as Kn, also with units of amps per volt squared. The third factor is the overdrive voltage, VOV equals VGS minus VTN. Once VGS is greater than VTN, an inversion channel forms. Increasing VGS attracts more channel charge, increases the conductance, and reduces the channel resistance. From the small VDS drain current equation, the ID versus VDS curve is linear, as shown in the figure. The slope of this line is the conductance GDS, which is proportional to the overdrive voltage VOV. Therefore, as VGS increases, GDS increases, and the corresponding resistance decreases. However, when VGS is below VT, no inversion channel is formed, so ideally there is no conducting current and the channel resistance is infinite. Because a conducting channel must be induced by a sufficiently large VGS, this type of MOSFET is called an enhancement type or enhancement mode MOSFET. If an NMOS device has a threshold voltage below 0 volts, then the channel already exists even when VGS equals 0. That type of device is called a depletion type or accumulation mode NMOSFET. Next, let us look at how an enhancement type NMOSFET behaves as VDS increases. When VGS is greater than VTN, an inversion electron channel already exists. The applied drain voltage VDS drops along the channel length, so the channel potential changes from 0 volts at the source to VDS at the drain. In other words, different positions along the channel are at different potentials. Near the source, the channel voltage is close to 0. Near the drain, it's close to VDS. Therefore, the gate-to-channel voltage, or the voltage across the oxide, also varies with position along the channel. At the source end, the channel voltage is 0, so the oxide voltage is VGS. At the drain end, the channel voltage is VDS, so the oxide voltage is VGS minus VDS. Since the inversion electron charge is proportional to the oxide voltage above threshold, the source side has more charge, while the drain side has less charge. This means the inversion charge is not uniformly distributed. Instead, the channel gradually becomes tapered, as shown in the figure. As VDS increases, the oxide voltage near the drain, VGS minus VDS, becomes smaller. This reduces the inversion charge near the drain end, narrows the channel there, and increases the channel resistance. Now we examine how the drain current ID changes as VDS increases. Earlier, we derived the small VDS result under the condition VDS is much smaller than VOV, where VOV equals VGS minus VT. In that case, the oxide voltage near the drain is still almost VGS, so the electron concentration in the channel is approximately uniform. This allowed us to write the drain current as charge per unit length times drift velocity, as shown in the equation. When VDS becomes larger, the carrier distribution in the channel becomes tapered. In the upper right plot, the blue line represents the channel voltage from the source, x equals 0, to the drain, x equals L. It increases from 0 to VDS and is approximately linear. The electron concentration at each point is proportional to the oxide voltage minus VT. At the source end, this voltage is VGS minus VT, or VOV. At the drain end, it becomes VOV minus VDS. Therefore, the drain end has less channel charge. If we use the average channel voltage, 1/2 VDS, then the average effective voltage controlling the channel charge becomes VOV minus 1/2 VDS. Replacing VOV by this average value gives the drain current formula for larger VDS. As shown in the equation, ID equals mu n C oxide to W over L multiplied by the quantity VOV minus 1/2 VDS and then multiplied by VDS. Compared with the small VDS equation, the voltage term is modified to account for the reduced average channel charge as VDS increases. If we substitute VOV equals VGS minus VT into that equation, we obtain ID equals mu n C oxide W over L times the quantity VGS minus VTN multiplied by VDS minus 1/2 VDS squared. When VDS is much smaller than VOV, the VDS squared term is much smaller than the product of VGS minus VT and VDS. Therefore, the squared term can be neglected, and the equation reduces to the earlier small VDS result. If we plot ID versus VDS, as shown in the lower left figure, the curve is almost linear when VDS is much smaller than VOV. As VDS increases, the curve becomes quadratic and reaches its maximum when VDS equals VOV. The operating region where VDS is less than VOV is called the triode region. When VDS equals VOV, the gate-to-drain voltage VGD equals VGS minus VDS, which becomes VT. Since the oxide voltage must exceed VT to maintain inversion charge, the channel charge at the drain end becomes 0. This is called pinch-off. Once VDS increases beyond VOV, the channel charge distribution changes very little and remains triangular, so the channel current is almost constant. This operating condition is called the saturation region. The drain voltage at which saturation begins is denoted VDS sat, and VDS sat equals VOV. The saturation region current is the maximum current reached in the triode region equation. By substituting VDS equals VOV into the triode region expression, we obtain ID equals 1/2 mu n C oxide W over L times VOV squared. Thus, when VDS is greater than VOV, the drain current becomes approximately saturated. For every gate voltage VGS greater than VT, there is a corresponding saturation voltage VDS sat equal to VOV. Therefore, if VDS is greater than VDS sat, or equivalently if VGD is less than VT, the MOSFET operates in the saturation region. If VDS is less than VDS sat, or VGD is greater than VT, it operates in the triode region, also called the linear region. Let us work through an example. Suppose the technology node has a minimum channel length L-min of 0.18 micrometers, oxide thickness T-oxide of 4 nanometers, electron mobility mu-n of 450 square centimeters per volt second, and threshold voltage Vt of 0.5 volts. First, we calculate the process-dependent parameters. The oxide capacitance density is C oxide equals epsilon oxide over T oxide, which equals 3.9 times 8.85 times 10 to the negative 14 divided by 4 times 10 to the negative 7. This gives C oxide equal to 8.63 times 10 to the negative 7 farads per square centimeter. Then Kn prime equals mu n times C oxide, which is about 388 microamps per volt squared. Now consider a MOSFET with W over L equal to 1.8 micrometers over 0.18 micrometers, operating in saturation with ID equal to 100 microamps. Using the saturation current equation, 100 microamps equals 1/2 times 0.388 milliamps per volt squared times 1.8 over 0.18 times VOV squared. Pay attention to the units. The current unit must match the unit used for Kn prime. Solving this gives VOV equal to about 0.23 volts. Once the process parameters in W over L are fixed, the saturation current is determined by VOV. Since VOV equals VGS minus VTN, and VTN is 0.5 volts, VGS is 0.23 volts 0.5 volts, which equals 0.73 volts. Therefore, the minimum drain to source voltage needed to enter saturation is VDS min equals VDS sat equals VOV, or 0.23 volts. If the MOSFET operates in the triode region with very small VDS, the channel can be modeled as an equivalent resistor. The resistance is the reciprocal of the conductance GDS, so R equals the inverse of Kn prime times W over L times VOV. Substituting the numbers gives R equals the inverse of 388 times 10 to the negative 6 times 10 times VOV. If the required channel resistance is 1,000 ohms, then VOV is about 0.26 volts, and VGS equals VOV plus VT, which is about 0.76 volts. Ideally, when VGS is below VTN, no current should flow. In a real device, however, a very small drain current still exists. This operating region is called the sub-threshold region. In an introductory electronics course, we usually do not analyze this region in detail, and we approximate it as the off state. After discussing N-MOSFET devices, we now introduce P-MOSFET devices. A PMOS device has the opposite doping structure. It is built on an N-type substrate with heavily doped P+ regions as source and drain. To form a P-type inversion channel, the gate voltage VGS must be negative. This negative voltage repels electrons from the semiconductor surface and attracts holes to form the inversion channel. The physical mechanism is the same as in NMOS, but the carrier type and voltage polarity are reversed. In an NMOS device, the channel carriers are negatively charged electrons. In a PMOS device, the channel carriers are positively charged holes. For a PMOSFET, the gate-to-source voltage must be more negative than the threshold voltage VTP to form the inversion channel. Since comparing negative numbers can be confusing, we often express the condition using magnitudes. Absolute VGS must be greater than absolute VTP. The PMOS process parameter is Kp prime equals mu P times C oxide, and Kp equals Kp prime times W over L. The hole mobility mu P is typically about 0.25 to 0.5 times the electron mobility mu N. In a PMOS device, holes move from source to drain, and because holes are positive carriers, the conventional current also flows from source to drain, opposite to the NMOS current direction. Modern integrated circuit design mainly uses complementary MOSFET technology, called CMOS. This means that both NMOS and PMOS devices are used together in the same circuit. As shown in the structure, the NMOS device is built in a P-type body, while the PMOS device is formed inside an intentionally doped N-type well, called the N-well, on the same wafer. Because a MOSFET structure is nearly symmetric from left to right, the circuit symbol uses an arrow to distinguish the source and drain terminals. The arrow indicates the normal direction of conventional current. For NMOS, current flows from drain to source, so the arrow points out of the source. For PMOS, current flows from source to drain, so the arrow points into the source. Although a MOSFET is a 4-terminal device, in most applications, the body and source are shorted together, so the common symbol usually shows only 3 terminals, G, S, and D. This concludes our introduction to the operating concept of metal-oxide semiconductor field effect transistors, or MOSFET devices. Please look forward to the next section. See you next time. Bye-bye.